Hi there. In this video, we're going to look at related rates, which is an application of some of the derivative rules we've been using. So let's jump right in. So the big idea here, what we're trying to talk about, is that in many physical situations, we study two quantities that are related. And the idea is that we discuss the rate of change of one quantity in terms of the rate of change of another. And this is called a related rates problem. And they're sort of like puzzles. So it's like a puzzle you have to solve. So I'm just going to do one example sort of all the way through with everything broken all the way down. Then I'll do two more examples that are a little more sort of like the speed that you should be working. So this first one, everything's broken all the way down. So a ladder 10 feet long rests against a vertical wall. If the bottom of the ladder slides away from the wall at a rate of 1.4 feet per second, how fast is the angle between the ladder and the ground changing when the bottom of the ladder is 8 feet from the wall? So this is what is known in calculus circles as the ladder problem. And it's sort of a really nice example of related rates problem. Notice that this is, just reading it, it seems impossible to solve. Because it just seems like there's too many moving parts, too many equations, too many unknowns. But we're going to show that it is actually possible, and in fact, not super duper difficult to solve it. So the first thing we're going to do is write down everything we know and everything we don't know. And then just sketch a picture. It doesn't have to be like very accurate. You just have to be able to label things. And you're allowed to name things whatever you want. So, you know, for a problem like this, it makes sense to label the distance along the ground as x and to label the height as y. That makes sense. And then the length of the ladder is 10, so we know that that's just 10. And of course, we're trying to find the angle. We're trying to find how fast the angle is changing. Right? So if you read, just kind of break down what it says. Length of the ladder, given. How fast it's moving in the x direction, given. And we want to know what is the rate of change of theta with respect to time. And that's what I wrote down here, right? What do we know? What do we not know? Once you do that, you have to write everything in terms of derivatives. So if it says the bottom of the ladder slides away from the wall at 1.4 feet per second, look at the picture and think what is the derivative, the physical quantity described in that statement that has to do with the derivative. Well, notice we have feet per second. As I pointed out in the previous slideshow, the units always tell you what the derivative is. So it's feet per second. So it's going to be distance per time. So time is going to be our independent variable. So it's just going to be dx dt. Right? So that's what we know. We know the speed that x is moving away. What do we not know? Well, we want to know the angle between the ladder and the ground. We want to know how fast that is changing. Well, that's going to be in radians per second. So it's going to be d theta dt. So you just write that stuff down, right? So we're given the rate of change of x per second, and we're trying to find the rate of change of theta per second, right? When x is 8 feet, right? And that's given at the bottom, right? When it's 8 feet away. Because theta is changing at a different rate depending on what x is, right? When the ladder first starts to slide, theta doesn't change very fast. You can see in the picture, right? But when x is very large, when x gets closer and closer to 10, theta starts to change faster and faster. So you want to write down, you want to really phrase it in this way. d theta dt when x equals 8 feet. Now we relate all the physical quantities that are not derivatives with any formula you can find. Well, this is the easiest one I could find that relates theta and x. It's just cosine, right? So looking at the picture, you can clearly see that cosine of theta is x over 10, right? So cosine adjacent over hypotenuse, right? So it's x over 10. So this is sort of like the setting up stage. We haven't done any calculus yet. And then you got to figure out a way to get these things to come from this. So what we do is just take the derivative of both sides with respect to t. So we just do d dt of both sides of the equation on the previous slide. And then don't forget the chain rule, right? Because this is similar to implicit differentiation where you get that chain rule, because theta is a function of time. So we have an outside function and an inside function, right? Theta itself is a function of time. So when we take the derivative of the outside, we have to take the derivative of the inside using the chain rule. Same thing over here, right? So now this one's a lot easier, but still, x is still a function, right? So the derivative of x with respect to time is just dx dt. So there's not really an inside function here, but you still have to do it, right? Okay, so now we have this quantity. Now look at what popped up here in purple. Those are the two things on the previous slide. One of them we know, the other one we don't know. All right, so we can plug in one of the things we know. All right, so just solve for the unknown quantity, right? Here, the unknown, what we're trying to find, just when you get this equation, just solve it for that so it becomes a function. And everything on the right side, you need to fill in. So d theta dt is what we're trying to find. dx dt we know. We could plug it in right now. But I don't want to plug it in until we figure out what this is. There's a sine theta over there. So this is where you use the last piece of information. There's one other given piece of information right here. We want to find d theta dt when x is 8 feet. So that means we're going to plug in x equals 8 here, and we have to find y because sine theta is opposite over hypotenuse. So we have to know what y is when x is 8. Okay, so we're just going to use the Pythagorean identity. You just solve for it, okay? There's many, many ways to do this. I know some of you are thinking, well, isn't that just a 6, 8, 10 right triangle? Sure, go ahead and use it. But as you're going to see in another problem, another example today, you're better off just writing everything out just in case you can't do it in your head. So I just use a Pythagorean identity. So when x equals 8, we know what cosine theta is, right? Right here. So we know cosine is 8 over 10, right? Just plug everything in. So I'm just using this. So 8 tenths squared. So sine squared plus 8 tenths squared equals 1. Go through the arithmetic on your own, and you get sine theta is 3/5, right? Take the square root, right? You get 6 tenths. 6 tenths is 3/5. So that's the last piece of information we need is sine theta. Plug everything into the equation, and you get negative 7/30 radians per second. So I do want this expressed this way. If you were an engineer or somebody, or like even, like if you're designing some system, you might want to flip that into degrees just so you understand exactly how fast the angle is changing. But for our purposes, that's good enough, right? Give me a fraction in lowest terms. Don't round it unless the homework says to round it. But on an exam, I want to see exact values. Now, this is not the only way to do this problem, but this is one way. It's the most easy to follow, and everything's broken all the way down. So here's the summary of the methods you should use. You don't have to do them in this order, but you basically have to do number 6 last. But you can do some of the other ones in sort of basically whatever order you want. Okay. Step 4 has to come after step 3. So, but other than that, you can basically put it in any order you want. So you should draw a picture, write down what is known and unknown, and then use names for variables that are easy to remember, like L for the length of a rectangle, because you're going to get to name stuff the way you want. And you can use X and Y. It doesn't make any difference, but you'll see when we get into because I'm going to do 2 more examples, you'll kind of see how you have to name things a certain way. Find an equation that relates the known and unknown quantities. Then take the derivative of both sides of that equation, and don't forget the chain rule, right? Because these are all going to be functions of t or functions of something. Solve for any remaining unknown values. So once you have your equation, you can look and see what in the equation you have and what you don't have. Anything you don't already have, you have to go get before you plug everything in. And then, of course, at the end, plug everything in to find the remaining unknown value, which will be your answer. All right, so here's example 1. So this is just sort of a nice typical problem of its type. So the length of a rectangle is increasing at a rate of 8 centimeters per second, and its width is increasing at a rate of 3 centimeters per second. When the length is 20 centimeters and the width is 10 centimeters, how fast is the area of the rectangle increasing? So draw a picture and just pick anything you want. So again, we kind of have an X and Y situation here. Now we have to relate. So we'll write down what's known and what's unknown. So here we're given dx dt is 8, dy dt is 3. All right, we're given those. What are we trying to find? We're trying to find the rate of change of the area when x is 20 and y is 10. So the equation, so there's a dA dt. So we want to relate all the physical quantities without derivatives. So we have a, x, y. Well, the area of a rectangle is just x times y, so that's pretty easy. And don't forget that x, y, and a are all functions of t. So when you take the derivative, you have to get a chain rule. So what's the derivative of a equals xy? Well, x and y are both functions, so we have to use the product rule when we take the derivative. Then I just evaluate all the derivatives, and don't forget the chain rule, right? A gets a chain rule, y gets a chain rule, x gets a chain rule. They're all functions of t. Now, this equation is already solved correctly, so we just have to plug in everything. We know x, we know dy dt, we know y, we know dx dt. Just plug everything in. We don't have to solve for any of the remaining values. And that's your answer. So when the geometry is simple like this, usually there's no problems. On your homework, some of the problems do have sort of complicated geometry. If you need to look up the formula for a area of a cone or the volume of a cone or surface area of a sphere, just look that stuff up, okay? I'm not going to ask you any crazy geometric questions on an exam. If I put a question like this on an exam, it's going to have a triangle, which is about half of the problems anyway, just triangles. All right, let's do another one. So as you're going to see, this one is much more complicated, but it's still the same type of problem. At noon, ship A is 100 kilometers west of ship B. Ship A is sailing south at 35 kilometers per hour, and ship B is sailing north at 25 kilometers per hour. How fast is the distance between the ships changing at 4 p.m.? So just before you flip to the next slides, before you look ahead, just think about how you would solve this. It's very difficult to imagine what's going on here unless you draw a picture, right? So there it is. So maybe that's what you imagined, maybe it isn't. But this represents every single thing we talked about in the previous slide, right? At noon, ship A is 100 kilometers west of ship B. Ship B is traveling north. Ship A is traveling south, right? And so you end up with this sort of like weird shape, but this is just the hypotenuse of a big triangle, right? When things run parallel, it doesn't matter where you measure it, right? And when you draw it as a big triangle, you can see that the big triangle just has a base 100 kilometers. The height here is just a plus b, which we don't know what that is yet. We're going to have to find that. And z is the hypotenuse. So we're really just solving a triangle problem. It doesn't make it easy. It just makes it, sort of gives us like a plan for how to solve it. So we were given the rate of change of both ships, right? A couple things. You're not required to label things as positive or negative, left and right, up and down, forward, backward, when you're doing these kind of problems that are geometric like this. A is moving south, so you could call that a negative value. But because we have a triangle, you solve the lengths of sides of triangles with the Pythagorean theorem. When you have the Pythagorean theorem, you just square everything, so it doesn't matter if you write it as negative or not. Okay, so don't worry about the tricky technical details, right? The ships are moving opposite directions, so the distance between them is just the sum of their speeds, right? So they're moving apart at 60 kilometers an hour. So we want to know how fast the distance between the ships is changing, which is dz dt, 4 hours after the initial passing, right? When they were 100 kilometers apart. And of course, Pythagorean theorem, right? So we have to find an equation that has a, b, and z in it, right? Well, this is 100. And this triangle has side length a plus b. So it's 100 squared plus a plus b squared. No, quantity a plus b squared equals z squared. Now we're going to take the derivative of this big Pythagorean theorem with the variables inside, the functions inside. So take the derivative of each side with respect to t, and don't forget that 100 is a constant, but this is a function of t, this is a function of t, and this is a function of t. So we get, so here's the derivative, right? Just doing d dt of both sides. This is going to be 0. But what's going to happen here when I take the derivative? Well, this is actually a double chain rule. The outside function is like u squared, right? It's a plus b squared. So we're going to bring the 2 out front. Then we have to take the derivative of the inside. Well, but a is a function of t. B is a function of t, so the chain rule will give us another copy of each of these, right? So we brought the 2 up, dropped the power by 1. That's your outside function. And then the inside function, because it is a double chain rule, the inside function, I went ahead and just did it. There's no reason to show that as an extra step. You know what the derivative of this is if you remember the chain rule, and you know what the derivative of this is. Plus, we need these things in the equation because they were given here. So you know that they're going to pop up in the equation because you already wrote down that we need them. And over here, same thing, right? Chain rule. Bring the 2 out front, 2z, and then the chain rule gives us dz dt. So do we know all of these quantities? We know this, we know this. We're trying to find this. We do not know a, b, and z. So now we need to look at what we have and find any remaining quantities. So I went ahead and solved it for dz dt. It doesn't matter if you do it this way or not. This is just the way I like to do it. But you can see that we need a, b, and z. So let's go get them. So how do we find a, b, and z when t equals 4 hours? Well, we know the speed. So a of 4, so that's a function. I'm not saying a times 4. I'm saying a of 4, because a is a function of t. That's the speed times the number of hours. So if it's 35 kilometers per hour for 4 hours, it has gone 140 kilometers. Same thing. B of 4, it's moving the opposite direction. Doesn't matter if you write it as positive or negative. So now we plug everything back into the Pythagorean theorem again. Now we know A, we know B. Plug everything in. Solve for z squared, and you get z is 260. So now we have all of the remaining pieces. We needed A when t was 4. We needed B when t was 4. And now we have z when t is 4. and you plug all this into the equation for dz dt. And I just ran it across the bottom. Just do it all on your calculator. And for this particular problem, I think the homework wants you to round to 2 decimal places. Just follow the directions on the homework. On an exam, a problem like this, I would tell you how many decimals to leave. And that's it. So notice we used that method. Draw a picture. Write down what you know and what you don't know. Relate all of the physical quantities with an equation. In this case, it was a Pythagorean theorem. Use that equation to find the rest of the unknown values, and then when you take the derivative of that equation, it lets you plug in all of the rates, your dA dt, your dz dt, whatever it happens to be. Then once you plug everything in, solve for what's left over. Whatever is left over is what you were trying to find. And that's it. So it's a pretty short section. The book exercises are really good. The homework tutor in this section has so many of the problems. So I just wrote down all of the problems that were good problems. If you wanted to see more different ways of doing these, because one thing about related rates, there's no template. Like every problem is a little bit different, right? The template is sort of that 6-step process for, organizing the information and solving. But there's no, every geometric construction is different, and all the variables have different names. So you might want to just look at more different ways to solve these problems. So highly recommend, the homework tutor in the media index here. And of course, you can check out the free online resources. There's lots of sort of extra stuff you can check out at the bottom there. Well, that's it for today. I'll see you guys next video. And if you have any questions, email me or post a question on the discussion forum. Until next video, see you later.